Well, good day, students. Here we have a one-factor or one-way ANOVA. Recall that factor here refers to the independent variable. So that means we have one independent variable in this research design. Now you can see the example here. This is from last week's lab. I'm not going to take time to read over this again. You can pause the video and read it if you'd like. But recall we have three groups in this design. We have a stereotype threat group and a neutral control group, and then finally an experimental control group. The data are presented here at the bottom, so you can see the ST, NC, and EC groups respectively. Now the dependent variable ranges from 0 to 30, and it represents the scores that the individuals have obtained on a quiz, on a 30-item quiz that was developed from the GRE verbal exam. Now the overall idea here is that the stereotype threat group should on average score lower than the NC and EC control groups. Of course, what we're going to do here is to make an inference to a population, or populations rather, so that in some arbitrarily defined populations, the ST individuals will score lower than the NC and EC individuals. So let's switch over to our ANOVA handout and begin working through this problem systematically by hand. So we see on our handout here when to use the one factor between subjects ANOVA. We see the assumptions and we see the hypotheses. So let's switch back over to PowerPoint and set up our hypotheses. So in this case we have three populations. These are individuals who can, in principle anyway, be assigned to the ST, NC, or EC groups. So these would be our three populations to which we're trying to generalize. So we have the means that we're trying to estimate and the standard deviations or variances. We're not given any of those values in the problem, so we're going to have to estimate those from the data. You see the hypotheses here. The null hypothesis is that the population means are all equal. The alternative hypothesis, in words, what we're testing here is that the population means are not all equal. And we write it like this just as a way to sort of summarize or write this idea in shorthand form, basically. So symbolically, that's what we're getting at here. The population means are not all equal. Now while we're here, let's go ahead and set up the table of descriptive statistics. So I'm going to take the raw data, so I'm going to go to the previous slide. I'm going to enter the raw data into my calculator and obtain the means, sample sizes, and standard deviations and variances. So here you see I've done that for the first, second, and third groups. I also have this total column over here. I'm going to talk about it in just a second. But first, let me remind you how to sort of just enter data into your calculator and get the mean, standard deviation. I'm going to use an online calculator quickly for group number 1 here. So here you can see I've copied the data for the first group into this little window. I select the calculate button, and we see there are 7 individuals in this group. The mean is 7.14, standard deviation is 2.54, and the variance, standard deviation squared, is 6.47 or 6.48. So there are the values in PowerPoint. Now let's move this window over, and I also want to take a look at the totals here. To get the totals, what you need to do is enter all of the numbers into your calculator. So let's take a look at how I did that. Here are all 22 values from all three groups entered into this little window, or entered into your calculator or Excel, or however you want to compute the means and variances and so forth. So I've entered all 22 individuals into the window. I select calculate. There's the sample size 22. The mean is 10.95. That's for everybody in the entire study. And then the standard deviation is 4.04 and the variance is 6.33. You'll need to get these totals. So make sure that you do this extra step. Enter all of the data from all of the groups into your calculator and get the mean for all the individuals and standard deviation for all the individuals as well. Those are going to be your totals as you see in the PowerPoint slide here. Now with our hypothesis set up and the table of descriptive statistics set, we can go ahead and begin working through NHST, or null hypothesis significance testing. So like what we've been doing in the past, we're going to have to get some sort of F observed, or some observed statistic rather, and compare it to a sampling distribution. In this case, we're dealing with the F distribution, the F test. The F distribution is skewed to the right, as you can see here, and this distribution changes its shape depending upon two things, depending upon how many groups you have and depending upon how many people are in your study. So if you look at the very bottom of this first page of your handout, you'll see there are 2 degrees of freedom values you need. You need DFA, and then you need DF error. And DFA is equal to A minus 1, and A just means the number of groups. DF error is equal to number of people in the entire sample, and grand minus A. So let's switch back to PowerPoint and look at those numbers. So using an alpha level of 0.5, in this example we had A-1 for the degrees of freedom. We had 3 groups, so 3 minus 1 is 2. DF error is n grand, again total number of people in the study minus A, so that's 22 people total minus the 3 groups, that gives us 19. Now for our F-crit value then, with 0.5 and 2 and 19 degrees of freedom, we'll go to the F table, and it's a skewed right distribution, so we're only going to get one value. We're not going to take plus or minus. It's not a symmetric distribution like the t-test. It's more like the chi-square, so we need to look up one value out of the F distribution. You can see on the PowerPoint what it is. It's 3.52, but let's take a look at the table quickly and see where I got that number. So here you can see the F distribution. I've magnified it a little bit, so it's a little bit fuzzy, but you can see the numerator degrees of freedom across the top. Okay, we have 2 for our study, and then DF2 down the side, the denominator degrees of freedom. That's the degrees of freedom error essentially. And so we find the intersection between 2, column number 2 here, and 19, and there we see the 3.5219. I'll just make it 3.52. So returning the PowerPoint here, that's where I got the 3.52 value. So now we have our critical value, and we can begin plugging and chugging through the formulas to get F observed. So let's switch back to the handout to see how we work through the formulas. So we're first testing the omnibus hypothesis. You can see the hypotheses repeated again here. We've already got our table of descriptive statistics set up. So now what we need to do is set up and fill in our source table. So I want you to draw a table out on your piece of paper just like you see here, and we're going to fill in the different parts of this table step by step. We're going to use the formula shown here. We've already got our degrees of freedom determined, but now we need sums of squares A, that's our independent variable or factor A, and then we'll need sums of squares error. So let's switch back to PowerPoint and plug and chug through these formulas and fill in that source table. So here you see I've done all the computations for SSA and SS error. So I've copied over the formulas, and you can see I've plugged in the sample sizes, the n's, so 7, 8, and 7. You can see I plugged in the means from the table of means, 7.14, 13.25, 12.14. Those are the 3 group means. And then you can see the grand mean, which is 10.95. So that's what I got from, again, entering all of the data into my calculator and got the grand, or the total mean there. And you plug and chug through that, you'll get 153.90. Now you can practice this on your calculator to see how to do these computations, make sure you know how to do them right. And then you can see sums of squares error is pretty straightforward. I took each sample size minus 1 and then just multiplied that by the respective variance. So you do the multiplication first, then you add up those results, and you get 189.20. Then what you want to do is plug that value into, or plug those values rather, into your source table. So you see the 153.9 there, the 189.2. Now the total is just the sum of those. So just add those 2 values up, and that's the total amount of variability in sums of squared units, right, for all of the data. Then you can just copy in your degrees of freedom. We already computed those, 2 and 19. Add those 2 values up. 19 plus 2 gives you 21. And then what you want to do is some basic division. Take 153.9, divide that by 2. So your sums of squares divided by your degrees of freedom gives you your mean squares value. Remember, mean squares is a variance. So I take a sums of squares, divide it by degrees of freedom, that gives me the variance. So that mean squares is the variance for the independent variable, 76.95. Then I take 189.2 and divide that by 19, and that gives me 9.96. So that's my variance due to error, unexplained variability rather. Now the last step is I take 76.95 and divide that by 9.96. That's the F ratio. So again, 76.95 divided by 9.96, and that gives me 7.73. You should work each of these out on your calculator and make sure you followed along with what I'm doing here, because you're going to need to create a source table and fill it in just like we've done here. Now what I have done in a nutshell is the F observed formula. So here I've written it out in the different versions, and in class we talked about it as mean squares between over mean squares within. That's just a different way of labeling the same formula. It's essentially mean squares for the independent variable over the mean squares error. And so here you can see I've plugged in the numbers, 153.9 divided by 2, 189.2 divided by 19, and then that gives you 76.95 over 9.96, and that is your F observed. Now that is statistically significant because it exceeds the 3.52, which was our critical value at alpha 05. And so that means we reject the null. We have a statistically significant finding. And it appears then that the three population means are not all equal. So that is the omnibus test, that overall there's something going on among those means. They're not all equal in the populations. Now let's quickly get p observed. So I'm going to switch over to the website that you can see on the PowerPoint slide here. It's also linked into our website. And let's get p observed. Notice our f observed is 7.73 and we have 2 and 19 degrees of freedom. We're going to need that. So let's switch over. So we'll enter our values here. So we had 2 and 19 degrees of freedom and our f value was 7.73, and we calculate and we get a p-value of 0.03496, so we'll just make it 0.003. So here I have it then, p-obs equals 0.003, and again that's less than 0.05, just another way of realizing that yes, this is a statistically significant finding. Now what about effect size? Effect size is fairly straightforward once you have your source tables set up. We'll use eta squared, and it is equal to the sums of squares A over sums of squares total. So 153.9 over 343.10, and that gives us 0.45. So 45% of the total variability in those numbers, in those data, can be explained by differences in the group means from the stereotype threat to the two experimental and control conditions. So 45% using Cohen's conventions is a whopping effect. All we needed was 0.14 or 14% for a large effect. So this is a massive effect size using Cohen's conventions. Then we move on to confidence intervals. And what we're going to do here is build a confidence interval around every mean. But just for practice, we're only going to do this for one mean. So I'm just going to pick the first mean, and I'm going to compute a confidence interval around that mean. But if you were publishing this research, you would want to do this for all three of the means. So here's the formula. X bar plus or minus, we get this F alpha with 1 and n minus 1 degrees of freedom, and then that's multiplied by the standard error of the mean for that group. So we take a look at the first group. The mean is 7.14, standard deviation is 2.55. There are 7 individuals in that group. Okay, where did I get the 5.99? The F alpha 1 n minus 1 are the degrees of freedom for this particular confidence interval. So we need to go back to our F table and look up an F value, an F critical value with 1 and 6 degrees of freedom. Again, 1 and n minus 1. There are 7 people, so 7 minus 1 is 6. So I need an F value with 1 and 6 degrees of freedom. So let's switch to the F table and look that value up. And so here we have 1 degree of freedom and 6. So right there, the intersection, 1 and 6 degrees of freedom is 5.9874. I'll just round it to 5.99. So that's where I got the 5.99 value then to plug into the confidence interval. So when you do the confidence intervals, you're going to have to look up the degrees of freedom with the 1 degree of freedom and then however many you have for that group. So here it's 7 people, 6 degrees of freedom. So 1 and 6 degrees of freedom, the F crit is 5.99. So with that value in place, then we take the square root of that, we do all the math here, and we get 7.14 plus or minus 2.36. So work that out, and you get a confidence interval from 5.78. This is around the ST group, the first group, all the way up to 9.50. And that's about a 4-point spread. The standard deviation for that group, as we can see, is 2.55, or this is kind of a slightly wide precision. Now again, if you were publishing this research, you would go ahead and do this exact same thing for the other two means using their respective sample sizes and standard deviations. But you only need to do one just to show me that you can work through the formulas and get the proper F crit value. So let's go ahead and move on then to the next stage in the ANOVA, or the analysis of variance. So let's go back to our handout and take a look at what we do next. So scrolling down here, we've gotten the effect size, we've got the 95% confidence interval, and now we move on to the pairwise comparisons. Here, these are like little mini independent samples t-tests. So we're going to look at 2 means at a time. Now in practice, you would look at all 3 pairwise comparisons, group 1 versus group 2, 1 versus 3, and 2 versus 3. But for our sake here, we're just going to work through one of these just to demonstrate how it's done. And we'll also get the effect size for that particular comparison. So we're going to take a look at the first and second groups here, the ST group versus the, I believe it's the UC group. Let's go back to the PowerPoint and take a look. So we see here it's actually the NC group, then the neutral control. So we have the stereotype threat group versus the neutral control, the first and second groups here. So our null hypothesis is that those two population means are the same. And then the alternative hypothesis is that there's an inequality going one way or the other. And we'll look at the means here at the end to see what the direction of the effect is. Now to run this comparison, we're going to need to adjust our F critical value because we're going to be running 3 different tests here, although we're only going to do 1 in practice here. But there would be 3 different tests that we could run. So we have to control type 1 error inflation. The 2 keys adjustment is one way to do that. So as you see on the handout, to get the new adjusted F crit value, you need degrees of freedom error, the number of groups, here it's 3, and the alpha level, which is 0.5. With those values in mind or in hand, you then go to the studentized range statistic, which is posted on the web. And let's switch over and take a look at that and find our new F critical value, because we're going to use it in this formula here. What we're getting is Q squared, or Q, which is the studentized range statistic. So let's switch to the table and take a look. So here's the studentized range statistic table for alpha 0.5. We have 3 groups here and 19 degrees of freedom. So we scan down and there we see 3.59. So 3 groups and 19 degrees of freedom. So the columns here are number of groups, not degrees of freedom, but number of groups. We have 3 groups and then 19 degrees of freedom. So 3.59 is our studentized range statistic. So let's go back to PowerPoint and plug and chug through. So we take that 3.59, we square that and divide by 2, and that gives us 6.44. That is our new F critical value. And notice it's higher than what we were using before. And that's making it more difficult for us to determine or declare rather statistical significance. That way we're controlling our type 1 error inflation because we're going to run multiple tests here. So with this new critical value in hand, we can go back to the formula sheet, pull the formulas off, and then plug and chug through. So here is the formula. F observed equals this stuff here. You plug and chug in the numbers for the first and second group. So the n's are 7 and 8 respectively. There are the 2 means for the group, 7.14 versus 13.25. Take the difference, square it, multiply that by 7 and 8, and then divide it by 15 times the mean squared error. So the mean squared error there I took from my source table, 9.96. Do all the math there and you get 13.99. Now that's a pretty substantial F value. It's larger than the 6.44, so it is statistically significant. So we reject the null hypothesis, and it appears that the ST population mean is lower than the NC population mean as predicted. So notice the 7.14 versus the 13.25, as you can see even in the equation there. So we have a significant finding in the predicted direction. Let's go ahead and get P observed for the 13.99. Now, whenever you run pairwise comparisons, the numerator degrees of freedom is 1. So we have 1 and 19 degrees of freedom here. Okay, so we'll go back to the calculator and we'll use 1 and 19 degrees of freedom for this pairwise comparison with the F value of 13.99. So we put in our 1 and 19 degrees of freedom, and then 13.99, calculate, and that gives us 00138. We'll just make it 001. So you can see that here, P observed is 001. Again, that's less than 0.5, just meaning that we've rejected the null hypothesis. Another way of seeing that, it's another way of making that conclusion, comparing P obs to P crit. Now for the effect size for this pairwise comparison, we use eta squared again, but now with this little formula based on the F observed. So you can plug and chug in. We take a 13.99, multiply by the 1 degree of freedom that we always have with a pairwise comparison for the numerator degrees of freedom, and then you're going to add in your DF error, which is 19. So when you plug and chug through that, you'll get 0.42. And again, that is a large effect using Cohen's conventions. I mean, it's a whopping effect, because all you needed was 0.14 for Cohen's conventions. So to complete the analysis, we compute all the confidence intervals, and we would also run through these pairwise comparisons for the other 2 comparisons, the ST group versus the EC group, and then the NC group versus the EC group. So we'd have 2 other comparisons that we would complete here, and then that would complete the analysis and make it ready for publication. But for us, we're done with this problem. We've rejected the omnibus null hypothesis, so the three population means are not all equal. When we started looking at pairs of means, we found that, as expected, the stereotype threat group performed more poorly than the neutral control group anyway, and that was a significant finding, suggesting again that those population means are not the same. The estimated mean, at least for the first group, was not estimated very precisely. The confidence interval was a bit wide. And then the effect size, though, was huge for the omnibus effect and for this particular pairwise comparison. Okay, so that wraps up the problem. Again, there's quite a bit to do here, but hopefully you can watch the video here, pause it where you need to, replay it, and work through a novel problem on your own. Certainly email me if you have any questions about this.